Relativity. It's something that surrounds us every day. You may have heard of it, but you also may not know what it really is. Well, I'm here to tell you that you do not have to be Einstein to understand it. In fact, I believe you could understand it yourself in just 10 minutes by watching this video. So, let's begin. Einstein, the icon of genius. You may know him from his incredible work in the photoelectric effect, or maybe just simply because he's known to be the smartest guy to ever have lived. Well, what really set his fame off was in 1905. Einstein had published his first theory of relativity, special relativity. 10 years later, in 1915, he had published his second theory of relativity, general relativity. Now these postulates were: the laws of physics are the same in all inertial frames of reference, and the speed of light in a vacuum has the same value of c in all inertial frames of reference. An inertial frame of reference is just what someone observes or considers to be at rest or in motion. Now for these theories and postulates to make sense, Einstein had created a new theory on space and time, which led to simplifying physics by treating space and time as the same thing. Space. Now, Einstein had never agreed with Newton's magical gravitational law, or if you like, theory. He had found it wasn't so complete. So Einstein started working on his own theory, and sure enough, he had solved it. He had discovered that objects with mass actually curve space-time. Imagine it like this. The natural motion of objects floating in space-time is to follow the simplest path. However, due to objects with mass curve space-time, it causes these objects to be attracted and move towards the most massive object. And this is what we know as gravity. Now, don't get confused with an object being referred to as larger and being referred to as being more massive. Larger means that it is physically bigger when looking at it. But referring to an object as being more massive means that it has more mass. It can still be smaller, but still be more massive by being more dense. So it is the objects with more mass that cause bigger curves in space-time. To understand relativity, we will first have to understand that there is no such thing as absolute motion nor absolute rest. Everything is relatively in motion or rest. For example, say you're in a train traveling 50 kilometers an hour, and your friend is standing on the ground observing you and the train as you go past. Now say you throw a ball whilst you're on the train in the same direction the train is going. The train is traveling at 50 kilometers an hour. However, relative to you, the train is stationary, and your friend is the one moving. When you threw your ball, it had a velocity of, let's say, 20 kilometers an hour. To you, observing the throw of the ball from the train makes the ball speed 20 kilometers an hour. However, your friend on the ground's observation would be the speed of the train plus the speed of the ball, resulting in the ball traveling at 70 kilometers an hour relative to your friend. Now, the difference between saying relative and just straight up saying to him is that, for example, you on the train have got a different observation towards the speed of the ball towards your friend's observation. So saying relative to him is stating that from your friend's perspective, the speed of the ball is traveling 70 kilometers an hour relative to him, but is still traveling 20 kilometers an hour relative to you. Now, I say there is no such thing as absolute motion nor rest, because the entire Earth is in motion, orbiting the Sun, making everything relative to us on Earth appear to be at rest, but is really in motion. And even so, the Sun orbits around the galaxy, and the galaxy even orbits around the universe. Therefore, everything moves relatively to each other. So nothing can be at rest nor be given an absolute motion / velocity / speed. This is what's called classical relativity. Classical relativity. It is probably one of the biggest parts of relativity, as it is the reason for so many things in everyday life. Here, let me give you an example. Let's say you're driving in a car and you're pouring some coffee. Now, even if you're going at 100 kilometers an hour, Nothing will happen, as you're traveling at a constant velocity. It's because you and the coffee are both traveling at the same velocity, which means that to both you and the coffee, there is no change. Therefore, you're basically at rest. But to someone observing you drive past, there is a change, as you and the coffee are traveling at 100 kilometers an hour and not at rest, or at least what they consider to be at rest. Okay, so we now understand the classical idea of relativity. But what makes relativity so revolutionary? Why is it said to be the most amazing theory of all time? Well, that's because of its strange consequences that are caused by it. But why it has become so famous and widely respected is because of one specific consequence, something called time dilation. Let's say you have two boxes named A and B, with two mirrors on each, opposite from each other, with a beam of light for both boxes bouncing between these mirrors. Now, let's pretend that box A is traveling at near light speed and box B is at rest. This means that the beam of box A, the one traveling at near light speed, is traveling a longer distance. If you can see, it is because it is traveling that it is required to bounce vertically to reach the opposite mirror, to then be able to bounce to the next mirror and repeat the pattern. So this actually means that it is traveling a longer distance than the box B, that just has to travel up and down. But because Einstein's theory states that the speed of light is the same in all inertial frames of reference, they should both still appear at the same velocity. Let's say we put a person in front of beam A, named John, and a person in front of beam B, named Matt. Because of Einstein's theory of relativity, both the beams will appear to travel at the same velocity from the observations of both John and Matt. So how can this be if light speed is the same in all inertial frames of reference, which is stated in Einstein's second postulate? Yet, when it races itself and travels a longer distance, it still manages to die. Doesn't this mean that it would require to travel faster? Well, no. You see, the only way that this can occur is if time slows down relatively to beam A, allowing it to travel a greater distance in the same time and become unequal with beam B. Now, this may sound like science fiction and be quite confusing to understand at first. So here is a simpler form. Say you're running from a T-Rex at a speed of 30 kilometers an hour, and you travel 1 kilometer in the time of 1 minute. You suddenly stop for another minute and then start again. You're still running at 30 kilometers an hour, but this time you traveled 100 kilometers an hour, but still in 1 minute. This is what time dilation does. But remember that time dilation really only occurs when near light speeds are achieved by time. If you still aren't following, look at it like this. Speed equals distance over time. So beam A's distance has become greater due to its speed increase we gave to it, which then means its time is to be greater because the beams both have the same speed, light speed, and will require to be equal using this equation. But if you increase the distance but keep the same time, then that would mean that its speed would be greater. So to correct this, we will have to increase the time as well, and therefore means that time slows down when object speeds are increased. This is called time dilation, one of the biggest parts of Einstein's theory of relativity. In part 2, the equation speed equals distance over time, the distance was increased, so we had to also increase the time, and therefore have time dilation. However, time does not dilate quite enough for this to work, so something else actually completes the job. It's called length contraction. Length contraction is as said by its name. It's the contraction of length. In the explanation of time dilation in part 2, box A not only experiences time dilation, but also contracts in size. With the distance increase having the time dilate, it still isn't enough to equal the required speed. But with the cause of length contraction, the distance becomes smaller and makes up for the time dilation shortage. Therefore, we can conclude that length contraction and time dilation actually work together to make sure that light speed stays the same for both observers, John and Matt. Time dilation was such a significant part to relativity, as it had widened our understanding towards how light behaves, in particular how quantum particles behave. This is such a big thing to the science world because when we start to travel outside of the solar system, it will be all because of Einstein's amazing explanation of time dilation that prepares us for the fact that all the quantum particles in our body that travel at near light speeds go through the same consequence of time dilation, and therefore means that when we humans travel out in space at near light speeds, our clocks will then travel slower to those on Earth. So after being in space for 10 years, relative to people on Earth, whilst travelling at 90% of the speed of light, to you it would have only felt like 4.35 years. And this is why it is so important. Now, in the early 18th century, scientists believed that light required a medium because they discovered that light travels like a wave, just like sound, another thing that travels like a wave, which does require a medium. A medium is just something that enables something else to travel through. So scientists called this medium the ether and used something called an interferometer device that would prove the existence of this ether. An interferometer device would measure the differences in light speed by detecting interference patterns that were recorded when they converged with an eyepiece. If these light beams were to converge with the eyepiece at different times, it would then mean that there is such thing as an ether. So, to understand this, we will have to first understand how an interferometer works. An interferometer has a beam of light that is emitted and would be split into two beams on two perpendicular arms, where they would then be bounced back by mirrors to converge with an eyepiece. This eyepiece detected the interference patterns that would occur when these beams of light would converge in the meeting point of the two perpendicular arms. However, there being a so-called ether would cause these beams to travel at different speeds, where they would then reach the eyepiece at different times, resulting in different interference pattern results. But without going into too much detail, they discovered that the eyepiece detected the same interference pattern, which meant that light did not require a medium, as its medium is basically empty space. Wow, so we now know that light doesn't require a medium, and that it has the same value in all inertial frames of reference. We also know what classical relativity, time dilation, and length contraction are. But what makes them so amazing? Well, it's because of their massive part into today's society. Let me ask you a question. Do you know what a phone is? How about television? And a computer? And even a GPS? How about a rocket? I'm sure you know what all of these things are, as today these are basic features that take place in our lives. Well, these are all here because of Einstein. Because of Einstein's incredible theory of relativity that helped us understand how almost everything works. And so it is this reason to why relativity is so amazing and revolutionary. So there we have it. Einstein's most amazing theory explained in just 10 minutes. Even though it's considered to be the most amazing theory, it doesn't mean it has to be a hard concept to understand. I hope you enjoyed this video and now have a better understanding of what relativity is. I hope you have a good day.